Hello, this is Jerry Pinter, and welcome to our lecture on Chapter 3, which covers vectors and motion in two dimensions. In this lecture, we will be covering Part 1 on vectors. So Chapter 3 is again going to be broken up into three different parts. Part 1, which we will discuss in this video, we'll talk about vectors. In Part 2, we'll deal with motion on a ramp or a slope, and then Part 3 covers projectile motion. I'll also mention that your textbook includes uniform circular motion in Chapter 3. However, we will not be covering uniform circular motion until we get to Chapter 6, and we will cover it in detail there. So let's begin our discussion of vectors. So this lecture is going to be basically a math lesson. We're not going to really do any physics per se. We're just going to learn how to deal with vectors. And then in parts 2 and 3, we'll apply what we learned about vectors to some physics problems with motion on a ramp and also projectile motion. So let's start our discussion by distinguishing between two types of mathematical quantities. One is called a scalar, and the other is called a vector. So what is a scalar? Well, a scalar is a quantity that has magnitude only. So examples of scalars that you're familiar with would be any number. So for example, the number 3 or the number pi is a scalar. Speed is a scalar. In other words, a scalar can be described by a single number. Later on in the course, we will talk about mass. The mass of an object is a scalar quantity. And temperature is another example of a scalar quantity. Now, what we're going to deal with in this section of this chapter are called vectors. And a vector is a quantity that has both magnitude and direction. So an example of a vector that we've already seen, we've talked about the displacement vector. The displacement had a magnitude, meaning how far something moved, but it also had a direction. Did it go in the positive direction or the negative direction? We also talked about velocity. Velocity is another example of a vector because velocity has a magnitude, which is the speed of the object, but velocity also tells us the direction of the object. In Chapter 2, we dealt with negative and positive velocities for directions. We also learned about acceleration. Acceleration is also a vector. So a vector is more complicated than a scalar quantity because it has more information embedded in it. It has to be described by at least two different numbers. It has to have a magnitude and a direction. So how do we deal with vectors, or how do we represent a vector? Well, the simplest way to think of a vector is just an arrow. So this arrow drawn here could represent the velocity vector of, for example, an airplane flying, through the sky, maybe going up into the air. And what this vector here, this diagram indicates, is the direction of the airplane, if this is its velocity vector, is just along the arrow. So that is very intuitive, and that makes sense. The arrow points in the direction of the vector. The length of the vector here that we draw, the length of this arrow, tells us the magnitude, which is the strength or the size of the vector. So for a velocity vector, the length here would tell us about the speed of the object, because that's the magnitude of the velocity vector. In working with vectors, we're going to have to do some basic vector mathematics. Let's start with an example of the simplest vector mathematics is just vector addition. So let's suppose we are given a picture of two vectors here. So we have vector D is going along this direction here, and vector E is indicated by this arrow going up here. Remember our notation for vectors. The name of the vector D has a little arrow over the top of it that tells us that this is a vector quantity. Likewise, the same for E. So the question here is, what is vector D plus vector E? So there are a couple different ways to add vectors, and we're going to actually learn 3 different ways in this lecture. The first one is called the tip-to-tail rule, and it's probably the most commonly used one in terms of adding vectors. So the idea here is that a vector can be moved around as long as its length and direction do not change. So in other words, we can take this vector e and we can slide it over here to where the tip of D is, right? So the tail of E, which is down here, we're going to move it over here and place it here. So you can see in this picture here, we've moved E and over to the tip of D. So this is why it's called the tip to tail method. Notice that E has exactly the same length up here, and it has exactly the same orientation. It's pointing upward in our picture. So this vector E over here is exactly the same as this vector E here. Okay, that's all we're doing here is moving it around. Once we do that, the sum of D plus E, which is called F in this diagram, we just draw a vector starting at the tail of D, and we go all the way up to the tip of E. And so this is the vector addition of these 2 vectors here. There's another way that is basically the same kind of concept, but I think it's a little more complicated. It's called the parallelogram rule. You can leave D and E in their original orientation shown up here, and you can sort of sketch out using dotted lines here a parallelogram using E and D as 2 of the sides. And then the resultant sum of D plus E is just the diagonal stretching across the parallelogram. So in either case, we get the addition of those 2 vectors. Later in this lecture, we're going to learn how to do this even more easily by using the components of the vectors, and we'll be adding vector components, but we'll save that for a little bit later. The next thing we're going to do with vector math is vector multiplication by scalar. So if we take a vector, for example, a vector A shown here, and if we multiply it by some scalar factor, let's just call it C. Now C is not a vector, C is just a number. C is a number like, let's say 2. So what happens when we multiply A by C? Well, what happens is A gets stretched by the amount given by C. So if C is 2, then when we multiply vector A by 2, we just stretch it twice as long. If C is 3, then we would stretch it 3 times as long. But notice that the orientation of the vector does not change, only the magnitude. So the multiplication by scalar changes the magnitude of a vector, not the direction. Now, one very important example of multiplication by scalar is what happens when we multiply a vector by -1. A -1, of course, is a scalar. It's a number. So here's the vector A shown here pointing in this direction. If we multiply A by -1, we get -A. All right, this is the opposite, basically, of this vector. So look at what -A is. It's the exact same length, exact same angle, but it's pointing in the opposite direction. So multiplying a vector by -1 just reverses the direction of the vector. Everything else stays the same. So here, this diagram down here kind of sums it all up here from vector multiplication by a scalar. If we start with some vector A, now A is pointing up in this direction. This vector down here represents 2A. All right, notice it's twice as long, but it's in the same direction. This vector down here represents -3A. Why? Well, first of all, the 3 makes it 3 times as long as this A up here, and the negative sign means it points in the opposite direction as the original vector up here. So make sure you understand these 3 results here, and you should be fine with vector multiplication by a scalar. Let's now turn to vector subtraction. So suppose we're given these 2 vectors, P and Q. So here's P pointing along this direction, and here's Q pointing in this direction. The question is, what is vector P minus vector Q? Well, the trick to doing vector subtraction is to turn subtraction into addition. Now, how do we do this? Well, we know how to add vectors, okay? So we have to somehow turn this into a vector addition problem, which we know how to do. Think about what we do with numbers. If we have a subtraction problem, like 5 minus 3, all right, which is obviously equal to 2, I can turn this subtraction problem into an addition problem by rewriting it as 5 plus negative 3, which is, of course, also equal to 2. So what we're going to do here, we're going to take Q, and we are going to find the opposite of Q. All right, instead of saying P minus Q, we're going to say P plus negative Q. So what is negative Q? Well, we know how to do that. Remember, if this is Q here pointing up and to the right, then minus Q points down and to the left. Okay, it's just in the opposite direction as Q. And we know how to add two vectors. We can add P, which is this vector here, to minus Q by using the tip to tail rule, and we get our result, which they called R in this diagram here. This vector R going from the tail of P to the tip of minus Q gives us the vector P minus Q. Now we're going to turn to something a little more powerful, and that is working with components of vectors. So this is technically what we're doing here is we're doing a vector decomposition, which means we're breaking up a vector into its constituent component vectors. The reason we're going to do this is because vectors are difficult to work with, and they point in arbitrary directions. So it's usually much easier to work with vector components because the components point along the x and the y axes. The vector components can be thought of as projections of a vector along the x and y axis, and I'll explain this shortly when we work with the diagram here. So any vector may be broken apart or decomposed into components which are the projections of the vector along the x and the y axis. And finally, a vector, we're going to see, is just the sum of its components. So let's look at this example here to make sense of this. So here's our vector A. A starts right here, and it points up to this region right here. Now, if we think of A, we can basically think of what is the height of A and what is the span of A along the x direction. So let's talk about this first. So the x component vector is parallel to the x-axis, and it's as long as A is horizontally. It gives us the horizontal length of the vector A. Another way to envision how to think of components is when we say a projection of a vector onto an axis, you could think about like shining a light down from above onto this vector and think about what its shadow would be. Well, this would be its shadow right here, a sub x. This is the x component vector of A. Likewise, vector A has a y component vector called a sub y, and a sub y is basically the vertical height of this vector. And again, you can think of this vector being projected along the y-axis here by, for example, maybe shining a light from over here on the right. So the light is shining, moving, the light rays are going to the left. A sub y would be the shadow of vector A projected onto the y-axis. So notice that these two component vectors, a sub x and a sub y, if we add them together, all right, a sub x plus a sub y, you can do that using the tip to tail rule, or you can do the parallelogram rule, whatever you want to do. You'll notice that a sub x plus a sub y gives us the vector A. So really what we're doing here is we're taking a vector A and we're breaking it up into its two component vectors, which are added together to give the resultant vector. So we now have some new terminology here. We have vectors, we have component vectors, and then finally we're going to introduce the components of the vector. So again, our vector in this example down here, we have a vector called A, which points in any direction. Okay, it's pointing up and to the right, as shown here. A can be decomposed into its two component vectors, AX and AY, which are shown here. AX, of course, is along the x-axis, and AY goes upward along the y-axis. These component vectors point along the x and y axes. All right, there is also something called the components, which are not vectors. They are just numbers. Notice there's no little arrow over a sub x or a sub y. So a sub x and a sub y are the components of vector A. They're a number that describes the component vector. It basically gives us the length and the direction given by the sign of the component vectors. So there's a lot of new terminology here, but it's actually quite simple. If we just look at the example here, this should clarify it. So here's our original vector A going like this. So let's draw its two component vectors. So a sub x starts here at the beginning of A, and we move over to the right just as far as the horizontal length of A. Notice that the length of this component vector, it goes from 1 to 4. So its length is 3. So the way we can write this, we can write a vector A as a pair of numbers. This is sort of like in math class when you learn about an XY coordinate pair. These are component pairs. So the first number here is going to be a sub x, which from this diagram you can see is 3. Right? It has a length of 3. The y component is the second number, and you can see it goes from y equal 1 up here to y equal 3, so it has a length or a component of 2. So these are the two components of the vector A, 3, 2. Let's look at another example of determining the components of a vector just to make sure this is very clear. So the first thing we can do is determine the magnitude or length of each component, and then determine the sign, if it's plus or minus, from the direction of the component vector. So this one's a little different. This is vector B, and it starts here again at 1, 1 on our graph here, and it points up and to the left up to this point right here. So you can see that the x component, or the x component vector of B, actually points to the left, because remember, B is pointing to the left. And how far does it go? Well, it goes from 1 here to -1, so it has a length of 2. So this component is 2, however, it's -2 because it's going to the left. Okay, so that's what the sign tells us, is that this vector in the x direction is going to the left. Likewise, the y component is going up with a length of 2, and since it's going up in the positive direction, it has there's no negative sign, it has a positive sign. So the vector B can be described as these components, -2 and +2. So our next bit of math lesson here is a review of trigonometry. And so I'm assuming that you've had trigonometry somewhere before in your courses, either in college or more likely you had it in high school. Basic trig is absolutely essential for doing physics. We really can't do any type of physics other than real basic physics without doing some trigonometry. So the bad news is you may have had some bad experiences or nightmares with trigonometry in the past, but the good news is we're going to keep it pretty simple. In fact, everything you need to know about trig is basically all shown on this one slide here. So let's go ahead with the review. So first of all, what is trig? Well, trigonometry is basically the mathematical relationships between the sides and angles of a right triangle. Okay, so right triangles are very important for working with vectors, and we're going to see them over and over in this course as we study physics. So, of course, a right triangle is characterized by the fact that it has a right angle. So here's our right angle down here, a 90-degree angle. And let's call this angle over here theta. All right, so here we have our right triangle. If this is the angle theta, then the side that's opposite of this angle is called the opposite side. Makes sense, right? And this side down here is close to the angle. In fact, it forms part of the angle here. So it's called the adjacent side. It's adjacent to the angle theta. And then, as you remember, the long side here of a right triangle is called the hypotenuse. So these three sides are abbreviated H, O, and A. So trig is all about the ratios of these various sides of the triangle and this angle here. So for example, the sine function is defined as follows. The sine of this angle theta is defined as the ratio of the opposite side over the hypotenuse. In other words, the length of this side divided by the length of this side gives us the sine of theta. All right, and we're going to use, of course, a calculator to calculate this. You're not going to have to do this by hand usually. And likewise, cosine of theta is defined as the adjacent side, this one here, divided by the hypotenuse here. And finally, the other important trig function that we're going to be using is the tangent function. The tangent of theta is defined as the opposite over the adjacent, so O over A. Now, we can also take these three relationships here for sine, cosine, and tangent, and we can basically invert them to solve for the angle, because a lot of times we want to know what the angle is. So in order to solve this for theta, basically we take the inverse of this sine theta function to give us theta. So we write this as follows. Theta is equal to the inverse sine of the opposite over the hypotenuse. This inverse sine, sine to the -1, is also called the arc sine. And depending on your calculator, there will be a button that either says sine with a little -1 up there, which means the inverse sine function, or your calculator may actually say arc sine, A-R-C-S-I-N. Likewise, for this function here, the cosine, we have theta is equal to the inverse cosine, or the arc cosine, of A over H. And finally, for the tangent of theta, theta is equal to the inverse tangent of the opposite over the adjacent. And then, of course, the last and arguably most important characteristic of any right triangle here is the Pythagorean theorem, which says that the adjacent side, A squared, plus the opposite side squared, O squared, gives us the hypotenuse, H squared. All right, and so we're going to use these relationships here on this slide here, which go with this picture here. We're going to be seeing this over and over in this course. And so if you're a little bit rusty on your trig, no need to worry. You're going to get plenty of practice in the homework and so forth. And as we get farther into the course, you'll become much more confident with using these basic trig functions. So in order to do this trig and the math involved with trigonometry, you're absolutely going to need a calculator. You'll need to have a scientific calculator. I would recommend something like this Casio solar-powered one here. Very cheap. You can get them, for about 12 bucks or something like this. The trig functions, make sure you can find them on your calculator and make sure you know how to use them. The sine, cosine, and tangent functions keys on this particular calculator are shown right here. And if you look, it's hard to see, I know, on this PowerPoint, but right above that in the yellow letters are the inverse sine, inverse cosine, and inverse tangent. And you access those by pressing the shift button before you press the, for example, the sine key there. So you will absolutely have to have a calculator that can do the basic trig functions. So if you don't have a calculator like this, now is the time to order one. All right, so let's look at some examples of using trig with vectors. So we're going to look at three different cases depending on what information is given to us and what we're trying to find. So the first case, case one, let's say we know the two components of the vector, a sub x and ay. So our example here, let's say a is given by the components 5 and 3. So remember what that means. That means, all right, here's vector a. The length of a along the horizontal is 5. That's our x component. And the y component is the height of the vector, the vertical height of the vector a, which is 3. Our goal here is to determine the magnitude of vector a and the direction theta of vector a. All right, so remember the length of this arrow is the magnitude of the vector. So how do we find that? Well, this is a perfect application of the Pythagorean theorem. We've got a right triangle here, right? You can see this. The reason we're using these component vectors is because they are at right angles of each other. The x component points along x, the y component along y. So this is why we're going to be able to use trig to work with vectors because of this right triangle. So the length of a, the magnitude of a, which is written like this sometimes, it can either be written as an a without the vector sign, a little arrow on top, or we put a with the arrow inside of these absolute value bars, which in vectors mean the magnitude of a. So how do we use Pythagorean theorem? Well, remember, all we do is square both of these sides down here. So the x component is 5, so I'm going to have 5 squared. And I add that to the y component, which is 3, so that's 3 squared. And we're going to, so we have 25 plus 9, which is 34. And remember, we're solving for a, not a squared, so we have to take the square root of 34, which turns out to be 5.83. So that's the length of our vector here. To find the direction theta, we're going to use the fact that theta is equal to the inverse tangent of the opposite side, which is 3, divided by the adjacent side, which is 5. So we have theta is equal to inverse tangent of 3 over 5. 3 over 5, do that first, that's 0.6. And then on your calculator, find the inverse tangent button. So you're going to press, you're going to enter 0.6 on your calculator and then hit the inverse tangent button. Again, you might have to hit the shift key to access that. And you should get 31, approximately 31 degrees. I rounded it here. So this is a good time to practice on your calculator and make sure you get these answers correct so that you know you're doing the right thing with your calculator. So here's case 2. Here's another example of using trig with vectors. Our second case here, let's suppose this time we're given the magnitude of a, and we're given the direction theta of the vector a, and we want to try to find the components of the vector. So in our example here, let's say a is 10. That's the magnitude of a. Remember, that's the length here of the hypotenuse is 10. And this angle theta down here is given to us as 30. We want to find this side down here, a sub x, and we want to find this side or component, a sub y. So to find, let's work on this one down here first. Remember that cosine of theta is defined as the adjacent side, which is a sub x, divided by the hypotenuse, which is the length a. So what we're trying to solve for is a sub x. So a sub x is equal to a, the hypotenuse, times the cosine of theta. So a, the length of a is 10, that was given, and theta was given as 30 degrees. So cosine of 30 degrees is 0.866. We multiply that by 10, and we get the x component of this vector is 8.66. Likewise, to find the y component, we use the fact that sine of theta is equal to the opposite over the hypotenuse. So we have a sub y, that's the opposite side here, divided by the hypotenuse. So a sub y, which is what we're trying to solve for, is therefore equal to the hypotenuse, a, times the sine of theta. All right, I'm just solving this for a sub y. And now we can plug in our numbers. Theta, again, is 30. The sine of 30 is 0.5. We multiply that by the hypotenuse 10, and we get a sub y is 5. So we have just found our two components here. This component is 8.66, and this component here is 5. One more example here, our last case here is where we know the magnitude of the vector, and we know one of its components, but not the other, and we don't know the angle. So for example, let's say we're told that the length of a vector is 7, and its x component is 5. So we want to find the angle of the vector, theta, and we want to find the y component of the vector. All right, so the first step here is let's go ahead and find the angle here. So remember that theta is equal to inverse cosine of a sub x over a. Now, why did I use the inverse cosine formula? Well, we know what a sub x is. We know the x component down here is 5. So I chose the trig function with the known numbers. So I have a sub x is 5, and of course I know that a is 7. All right, so that means I'm going to use the cosine, inverse cosine function. So theta is equal to the inverse cosine of 5 over 7. First, figure that out on your calculator. It's 0.714. And then find the inverse cosine of 0.714, and you should get 44.4 degrees. So again, I would recommend doing this on your calculator to make sure that you are doing these trig functions correctly. The second step, or last step here, is to find the component a sub y. Well, a sub y is equal to the hypotenuse a times the sine of theta. We actually did this in the previous slide. So here we know our theta is 44.4. That was what we found out here in step 1. And we're going to take the sine of that angle and then multiply the result by 7, and you should get 4.9. So there is our unknown y component of this vector A. One of the nice things about working with vector components is that when we want to do math with them, such as adding or subtracting vectors, it's very simple to do. We don't have to use trig at all. So if we have two vectors in this diagram here, you can see there's a vector A shown here and a vector B shown here. If we want to add these two vectors using the tip to tail method, I'm going to take vector B down here and I'm going to slide it up here. It's now shown in black up here. So the resultant vector A plus B is, by tip to tail method, we go from the tail of A to the tip of B. So this red vector here is the total sum of vectors A plus B. But notice what happens here. We have the x component of C, which means from the origin all the way over to here, is just the x component of A, which is A sub x, plus the x component of B, B sub x. All right, so our x component of the resultant vector is found by simply adding the two x components from A and B together. Likewise, for the y component of vector C, all we have to do is add the two numbers for the respective y components of the vectors A and B. So let's do some examples that will help clarify this, and you'll see how simple this actually is. So suppose we're given two vectors, and we're working now with their components. So the nice thing here again is we don't have to use any trig. There's not going to be any sines or cosines or anything like that, or no angles. So vector A is given as 3, 5. So remember, these are the two components of vector A. The x component is 3, the y component is 5. Likewise, we have vector B. It has an x component of -2, and a y component of +1. So the first question here is, what is vector A plus B? So instead of doing tip to tail method, all we have to do is add the components together. So notice I have a 3 here and a -2 here. So I'm going to add 3 plus -2 to get 1. That is our x component of the sum. For the y components, I've got 5 here and 1 there. So 5 plus 1 gives me 6. So here is my sum. The sum vector is 1, 6. So very, very convenient and simple working with components. Let's do subtraction. What is vector A minus vector B? So A minus B, all we do is subtract the components. So I have 3, and I have to subtract -2. So notice 3 minus -2, these two negative signs or minus signs cancel each other. So I end up with 3 plus 2, which is 5. And then for the y components, I have to subtract them. I have 5 minus 1, which gives me 4. So here is the vector subtraction, A minus B. The components are 5, 4. And we can, do a little bit more tricky problem that involves multiplication by scalars as well. So for example, what is 3a minus 2b? Well, let's do the multiplication by scalars first. We know that a is 3, 5. So 3a is going to be 9, 15. I just multiplied each of these numbers up here by 3. And likewise, 2b is equal to 2 times -2, which gives me -4, and 2 times 1 gives me 2. So now I've got the vector 3a and 2b. I just need to subtract them from each other. All right, so I'm going to have 9. I'm going to do the x components first. 9 minus a -4. All right, 9 minus -4 gives me positive 13. And then for the y components, I have 15 here minus 2. So 15 minus 2 gives me the y component, which is also 13. So the vector 3a minus 2b is a vector with a x component of 13 and a y component of 13. So this concludes our this first part of this chapter, and we now have basically all the vector mathematics and trig that we're going to be able to use going forward in this course. Until next time, have a good day.